Joint work between my advisor, Brian Williams, and myself, and two summer students in our lab, Gerard Kelly and Michael Sheehy, that helped me with the experimental results. Okay, so we give motivation, go through problem statement, overview of problem approach, talk about prior work, then go into the technical innovations, experimental results, and conclusions. Okay, so the motivation. In our lab, we deal a lot with robotics in uncertain and dynamic environments. So what we'd like to do is to verify the behavior of robots in a dynamic and uncertain environment, and also through failure. And by verification and planning are kind of the same. So how do we plan in a dynamic and uncertain environment? And how do we plan through failure? And also, in addition to that, we like to write specifications of the behavior in a robotic engineer's or an embedded systems engineer native language. Okay, so kind of a high-level problem statement here. Engineers program embedded systems with reactive programs. So we have if else, until, try catch. If you're actually working with a robot, you'll be using this stuff. So conditional execution, iteration, exception handling, the obvious sequential and parallel composition. But specification languages don't look anything like this. So how can we fix that? Well, we can try to start from a reactive programming language with the constructs that embedded programmers already use, and then add in a timing specification construct, the simple or metric timing constraint that we use in the planning community. So this is what I'm going to call the reactive model-based programming language. The idea is to pick out the reactive programming constructs that are kind of ubiquitous across programming languages. So the main three, and add in a simple timing construct and try to do planning over that. Okay, so two important observations can be made regarding this approach. We have the building blocks to provide verification of timing constraints through failure. So if you imagine these are the constructs we can program in. We have the regular constructs you're always using, and then we have this timing constraint, which is kind of like an assertion in the program that we assert that whatever these things do, they have to obey these timing constraints. So we can have like a timing constraint, and then inside of that we have nested and exception handling, and inside of that nested timing constraint again. And so if we're able to honor this syntax, then we should be able to provide verification through failures. The second one is that we're writing timing specifications in a robotic engineer's native language, reactive programs. Okay, so a simple example. All right, so we like to give the dog a bone, and those familiar with American culture, this dog likes tacos. So we kind of give a specification of the desired behavior here, which is to go to waypoint 1, waypoint 2, waypoint 3 in at most 40 seconds. And if the operating region is violated, which we kind of denote by a box here in state space, then go home and start over. So if it gets knocked, then go home and start over. We see here, like, we took data from the arm, and here we kind of knocked it out just manually as it was going along, and these represent paths of it going back to its home position. If there's an obstacle on the path, go waypoint 2 north. So we put in a couple of contingencies where if there was an obstacle in the middle of its path, then it would go above the obstacle. And then finally, try to accomplish this up to 3 times before giving up and remaining in the home position. Kind of the point here is that we like to provide a guarantee that after 40 seconds, either the taco is delivered to the dog or the hand is back in the home position. So the arm doesn't, remain off somewhere else in state space. The dog gets hungry, bites the hand, it'd be really bad. So we want to guarantee that the hand is either in the home position or the goal has been accomplished after 40 seconds. Okay, so doing that in the programming language that we just defined, or the specification language, the first thing we can do is just to provide a normal go from waypoint 1 to waypoint 2, waypoint 3, our primitive activities. We have timing constraints associated with the time points the executive can choose for how long that duration is going to take. Next, we add in some of these reactive constructs. So to achieve these other desired goals we have up here. Next, we can try to achieve this, but if we fail, then we catch the failure and go back to the home position. Finally, if there's an obstacle in the way, go waypoint 2 north instead of waypoint 2. In the third construct we have in the language is until. So we can try this entire subprogram up to 2 or 3 times until we reach the goal condition of in waypoint 3. So the point here is that we have an executive that's going to try to execute this program. And as the program is executing, the executive gets to pick the time points for when it's going to when these activities should complete. So as things happen and the program unfolds, you learn information about whether obstacles are in the way or not, and then you get to pick the time points such that your timing goal of 40 seconds is met as you're executing the program. So that's the concept of dynamic controllability for reactive programs. Okay, so I showed you the language. Now, how do we accomplish dynamic controllability? So it's going to be a 2-step approach. First is language reformulation, and the second is dynamic execution. So language reformulation is we go from this reactive language that we defined into a temporal constraint graph representation that our community is used to dealing with. The second one is a dynamic execution strategy, where, which is familiar in our community. You start with a temporal constraint graph. You can think of it, SDP, DTPs, PPNs, whatever. Then you have a constraint solver, which is usually it's a constraint satisfaction problem where each of the candidates is a simple temporal problem. So your constraint solver is a CSP and like an all pair shortest path algorithm. And then what happens is you come up with if you come up with a solution to the problem, then you call it a dynamically executable constraint representation of the problem, which can be executed dynamically online. So the key innovation in my paper is to add in an and/or graph representation instead of a CSP representation to model the reactive elements. And then the key is when the constraint solver solves it, you end up with a solved constraint representation, but also an underlying and/or solution subtree that allows us to dynamically execute programs with reactive elements. I'll go into that in a bit. Okay, so prior work in the area. So those familiar with all of the temporal constraint models, we study how to execute networks of temporally flexible constraints such that no timing constraints are violated. So we start out with controllable timing durations. We add in uncontrollable timing durations. Now to do things that we want to, like conditional execution, uncertain environment, we want to add in controllable choice and uncontrollable choice. And to get exceptions or failures, we choose to view a failure as an uncertain event, or an uncertain choice at an uncertain time. So it's an uncontrollable choice node that happens at a time that we can't predict. And therefore, so if we have all 3 of these, then we can model failures in temporal constraint network. So that's the focus of this paper. Okay, so technical innovations. How do we go from the language specification to temporal constraint graph representation? So this part is pretty straightforward and builds upon prior work in our group. The point here is to go from the reactive programming constructs to a semantics in terms of, we call them hierarchical constraint automaton, but they're really just finite state machines, state flow diagrams, whatever you want to think of them as. The point is that these automata explicitly represent the control flow implicitly implied by the language syntax. So this is from the simple ARM example. This is the automaton. So you kind of see it goes to waypoint 1, and then it like tries, to do 2. There's an obstacle, and it goes through the automaton. We don't do anything fancy to get to the temporal constraint graph representation. We just unfold it. So so a loop would have one iteration of the loop, 2 iterations of the loop, 3 iterations of the loop, and it might be any of those. So that's how we unfold it to get to our constraint graph representation. And then the result of the unfolding is a temporal constraint graph consisting of the following elements. So you'll have controllable time points, uncontrollable time points, controllable choice nodes, uncontrollable choice nodes. and then the controllable time constraint, or arcs, and uncontrollable time constraints, arcs that go along with the time point nodes. So this is an example network of the simple ARM example. You can see all the different nodes in there. Okay, so that was how we went from the language representation to a temporal constraint graph. So next I'm going to describe what these and/or trees are. It's nothing too complicated for people that study game trees and stuff like that. Okay, so here's a really simple example of a game tree, an and/or search tree. Consider a two-player game. You get to choose either 0 or 2, and if the additive total at the end is 2, then you win. But the villain has a choice of choosing 0 or 2, so he can foil you, depending on who gets to go first. So terminal nodes are marked solved or unsolved. Here we denote them by red or green. Here are all the possible outcomes of the game. If we choose 0 and the villain chooses 0, the outcome is 0, so we lose, etc. Okay. So an and/or search tree is a graphical problem representation used to determine whether or not a dynamic decision policy exists in which the hero always wins. So that's a complex way of saying that you win, you're guaranteed to win the game. So if the villain has to go first, you see that we have the choice of choosing the opposite choice of the villain to win. So kind of the details are AND states represent problem decomposition into subproblems, all of which need to be solved. And when we're playing against an adversary, we have to be robust to all of the choices the adversary might choose because we're not in control of the adversary. And then for OR states, we only have to be robust to one of them because we're in control of which choice is made at that. Okay, so what's an AND/OR solution subtree? Well, I mean, obviously this is the solution to this AND/OR tree. The villain chooses 0, we choose 2. Villain chooses 2, we choose 0. What are the properties of this tree? All terminal nodes have to be solved. Each AND node in a solution subtree has to have all of its child nodes in a solution subtree. Just, as I just described, we're not in control of what the villain does. Each OR node only has to have one. So if it's possible to construct a tree with these properties from the original AND/OR search tree, then we have a solution to the problem. We have an AND/OR solution subtree. So if we look at the alternative example where the hero goes first and the villain goes second, then the villain can foil us by choosing 0 if we choose 0 or 2 if we choose 2. So for this case, there is no tree from subtree in this tree that satisfies these properties. So this is how we are going to model the reactive constructs and make sure that we have a dynamically controllable policy for executing the program. Okay, so that was AND/OR trees. Now how do we map from AND/OR trees, or from the language constructs into the AND/OR trees? So we create a mapping for each construct. So sequence is the generative case where it doesn't matter if it's AND or OR because you're just doing one thing and one after the other. Our parallel construct for executing things in parallel is an AND construct because we have to do everything in parallel. Again, the until construct is an AND branch because we don't know, we're not in control of the condition on when until the goal condition is satisfied. So we have to be robust to all in loops of the program. I guess an important side note here is that we have to choose a finite number in our program, otherwise it will be infinite. Okay, so the other constructs, if else, we're not in control of these conditions on the environment, so we assume we have to be robust to both outcomes. We have the choice operator, which is we put in alternative choices that we can make into the program. So for those, we only have to be robust to one, so that's an OR node. The exception handling construct is kind of interesting. So you get when we take an exception or a nominal try or an exception block, we're in the try block, and if the exception gets called, then we fall out into a catch phrase, and we model that by an uncontrollable or an AND branch between the nominal branch and then all of the conditions that might be invoked. So that's something we're not in control of, so it's an AND branch. And then in the dynamic controllability algorithm in the paper, to improve tractability, we put a number in. We're only robust to in false at runtime. So when we're doing the dynamic controllability calculation, once we get to in try catch construct, we only model the nominal branch after that to improve to improve the tractability. So that way we're constructing programs that are robust to almost in faults at runtime. Okay, so it gets a little bit trickier. It's not just a straight mapping from language elements to and/or trees, because the language constructs can interact. And I gave a simple example of this, one of the examples, which is, imagine we have, this is like an if-else construct or a try-catch construct, that we're not in control of what happens at this branch. But these are all controllable timing nodes. These are all controllable timing arcs. So we're in control of when this observation is taken relative to all of these nodes. So if you imagine that we're holding on to this, we can move it anywhere we want along here and then take the observation. Then we have to be robust to it. So kind of in the and/or tree representation of that, for at least one node ordering of this one relative to these, both of these outcomes have to be consistent. So you can think of it as an OR node. We get to choose between where this node is relative to this one, this one, this one, this one. So that's 4 branches where we only have to be robust to 1. And then we have a binary and branch after that. And the reason that just intuitively the reason we need that is that say that we execute this observation where it scans right here. Then after we make that observation, we can choose different times for these controllable branches to try to compensate for which of these paths gets taken. So it's important where this node executes relative to all of these. So you come up with extra branches in your and/or diagram. So that's kind of an important difference between these types of networks and ones where you're not dynamically learning things at runtime. Okay, so now that you've kind of seen how we go from the language into the and/or tree representation, maybe this diagram will make a little bit more sense. So for people that are familiar with the area, you start with a temporal constraint graph. You have a model of it as a CSP in a constraint solver called pair shortest path. But here we have an and/or graph instead of a CSP. And the output is a dynamically executable constraint representation, which underneath has an and/or solution subtree. Okay, experimental results. So we created 4 categories of plans to test for dynamic controllability. And each of the programs had 3 parallel threads of execution. We randomly chose RMPL constructs in each one. So we increased the complexity of the plans from category 1 to category 4. So in category 1, we only had 1 construct within each parallel branch. Category 2, we had 2 nested constructs. Category 3, 3 nested constructs, and 4 nested constructs. So in this category, a plan might look like there are 3 branches where in one of the branches it might have a nested controllable choice within an uncontrollable choice within a try-catch block. And then there would be 4 of them in this thing. And then kind of the key result from this is that regardless of how complex the program was, the computation time was driven by the number of faults we wish to be robust to. And you can think of that intuitively as you've got a constraint satisfaction problem, and every time you get rid of a fault you want to be robust to, you're removing a variable from the problem. So, and because the and/or trees don't branch one-to-one with the constructs, you're actually removing several variables for each fault you don't want to be robust to. So this is kind of an intuitively easy result. Okay, so conclusions. Our motivations were to write specifications in a robotic engineer's native language. So the way we try to do that is we extend dynamic controllability of temporally flexible plans to temporally flexible reactive programs. Another thing we'd like to do is verification of behavior in a dynamic and uncertain environment. And the way we accomplish that is an algorithm which frames dynamic controllability of RMPL programs as an and/or search tree over possible program executions. And finally, verification of behavior through failure. In our approach, handled exceptions are considered successful program executions. And dynamic controllability corresponds to a guarantee that the program will execute to completion despite runtime constraint violations. And finally, to improve tractability, an approach is developed called in-fault dynamic controllability, which ensures robustness to at most n exceptions at runtime. And that's it.
If I understood what you were saying, after n faults, you don't look for a fault condition anymore when you're unfolding your tree?
Right.
Do you have a method for addressing, I assume that's the first n, but it's certainly conceivable if I'm trying to verify something like this that the complex faults that I really want to deal with are later, right? So if I stop looking for faults, is there a way to vary which n I'm getting when I'm looking at the
okay, so the n is nested faults. So if n is 1, then you consider all one fault cases. N of 2 means that you're already down a fault branch, and then you go down another fault branch. We don't care about that one. So was that your question, or so you can?
Well,
but you're saying that maybe some you want to be robust to some triple faults and not.
I want to be robust to a triple fault, but I don't want to be robust to the first possible 3 triple faults.
Right.
I fault on the first branch, but then I execute 6 branches just fine, and then I get 2 more.
Right. Yeah. So you can imagine a lot of domain-specific cases where you really prefer to keep some exceptions rather than others. And yeah, I mean, you could like specially tailor the compilation algorithm to care about the ones you care about if you wanted to. But you have to know for that specific case. But yeah, you can do that. You could compile a program that took into account whatever exceptions you wanted. So imagine that you just write up the program and you only put in the exceptions you want, and then you put into infinity. Then you would compile the program and everything you care about. The only point about this is say the user gives you a control program that's really complicated, but the executive can only handle faults up to n equals 3, and then it has a bound on itself where it can say, okay, you wanted to handle all these faults, but I can only handle up to triple faults, and then it gets too complicated. So.
You have this AND/OR tree, so how do you solve it? Do you use like AO star or the AND/OR graph, right?
Right. Yeah. So because we compile everything out into temporal constraints, because everything is compiled out into temporal constraints, the only thing we're really left with is disjunctions in the plan. So I use a conditional CSP solver, and at every solution point it solves an alternate choice path problem. I don't know if that answers your question. I don't really remember what the AO star is.
Because the thing that I watch is like you are not dealing with an AND/OR problem per se. It's more like a game problem.
Right.
Where you want a winning strategy. So you can use alphabet pruning or some of the more fancy algorithms like that.
Right. Yeah. So that's right. So I just started looking into the game theory stuff, and I think that's definitely where I should go. And I think that's also the best way to handle the uncertain durations. In my paper, the way I handled uncertain durations is I just discretized the times and considered an uncertain duration as a disjunction of small controllable durations, which is not ideally the right way to go. I think if you use a game tree, you can get around that.
Okay, sorry, but we'll have to wrap up. Other people are waiting for us, so let's thank again the speakers.